We'll start moving to your test. Please make a note what you need for the exam tomorrow. You just have a single period, 40 minutes. So you do not need to bring any other physics things except these here on the screen. You need to bring a pen, a pencil, a ruler, and a calculator. That's it. That is all you will need to supply of your own stuff. For tomorrow, there is no sharing of materials. I don't loan them out unless you have something that's defective during the test, like your calculator dies during the exam, then I'll loan you one. But if you forgot it, oh well. Okay, so please make sure you bring your own stuff. If you don't have it and you are sharing with somebody during the test, both you and the person you're sharing with get zeros on the test because it's cheating. And you're handing stuff back and forth between another student. I'm not paying 100% attention to what you're sharing back and forth. It really doesn't matter. You're not supposed to be passing things back and forth between students. Okay. Any questions on that? Okay. It's a full 40 minutes tomorrow. So we're not doing anything else. You finish early, you turn it in, and then you can work on something for another class. But that's it. Okay. All right, so let's go over the review assignment, starting on page 21. What I'd like to do first is give you answers to everything, and then take questions at the end, okay? So just correct your work first, and then I'll take answers at the end. Okay, so in number 1, they asked you to label the targets. So the target on the left is target C. This is target A, this is target D, and the one on the right is target B. Those go with the descriptions written here, okay? Number 2, A, you were asked to measure the length of this pencil with your ruler. First thing I'm checking for, do you have the right precision? Did you measure out to the hundredths place? If so, now I can check the number that you wrote. The number you wrote should have been between 6.20 and 6.60 centimeters. When you're taking your test, you're not going to do this part. You're just giving me an answer. This is what I have on my key, so I know what range I'm allowing you. Okay? So you're giving me an answer somewhere between 6.20 and 6.60 centimeters. If you put 6.6 centimeters, it's marked wrong, because it didn't go to the right decimal place. You didn't measure with the correct precision of the ruler that you have. This measurement has 3 sig figs. Letter B, this pen, accepted answer is 10.25 centimeters, again to the hundredths place. I'm going to give 0.2 of a centimeter leeway. So I think between 10.05 and 10.45 centimeters would be acceptable. Those measurements all have 4 sig figs. Number 3, this measurement has 2 significant figures, and in scientific notation, you should have written 3.2 times 10 to the negative 3 millimeters. Letter B, this measurement also has 3 sig figs. In scientific notation, it's 3.81 times 10 to the 4 kilograms. Letter C, this measurement has 3 significant figures. It is 7.01 times 10 to the negative 4 seconds. Letter D, this has 4 significant figures. In scientific notation. With the 4 sig figs, you would write 3.600 times 10 to the 1 meter per second. Letter E has 1 significant figure. It is 4 times 10 to the 2nd power, capital N. Number 4, show these conversions. Okay, so the first thing we have to do is look up the prefixes. Milli is 10 to the negative 3rd power. Kilo is 10 to the 3rd power. You should be able to state that when you start your problem. Now we use factor label method, putting the given value over 1. That is 55 milliseconds over 1. You're now going to multiply by a fraction to get rid of the milli. That means milli goes in the denominator, its power of 10 in the numerator. So milli in the bottom and 1 times 10 to the negative 3 in the numerator. The next fraction multiplies the kilo by the remaining second that's there. So that is kilo over 1 times 10 to the third power. You go to the calculator, type it all in correctly. Hopefully you get 5.5 times 10 to the negative 6 kiloseconds. Letter B, now we need to convert 81 nanometers to gigameters. So we're going to put the given value over 1. That is 81 nanometers over 1. So the nano is 10 to the negative 9. So 1 times 10 to the negative 9 over nano. And then we have giga over 1 times 10 to the 9th power. Gives us an answer of 8.1 times 10 to the negative 17th power gigameters. Part C, we need to convert decigrams to picograms. Deci's 10 to the negative 1 power, pico's 10 to the negative 12th power. So again, 12 decigrams over 1. Then we have 1 times 10 to the negative 1 over deci, and pico over 1 times 10 to the negative 12. Calculator answer is 1.2 times 10 to the 12th power, and the units are picograms. All right, number 5, all the algebra. Let's see if you can do the algebraic manipulation. Solve each of these equations for the variable x. Let's start with the equation PES is 1/2 times k times x squared. Notice there's no addition or subtraction signs in that equation, so we are not doing any addition or subtraction. It's all division or multiplication. So I'm going to divide both sides by the half k first. So when I divide both sides by half of k, I end up with PES over half of k is x squared. Now I have to undo the square by taking the square root of each side. And when I do that, I either end up with x equals the square root of PES over half of k, or x is the square root of 2 times PES over k. Dividing by a half is the same as multiplying by 2. So you could write this either way. Letter B, we have the equation F is negative k times x. To solve that for x, we have to undo the multiplication between the negative k and the x, which means we're going to divide both sides by negative k, which gives us F over negative k is x. Letter C, we have 3 plus x over y squared equals z. First thing I'm going to do is get the y squared out of the denominator, multiply both sides by y squared. That gives me 3 plus x is z times y squared. Now I want the x by itself, which means I have to get the 3 out of here. It's being added to x, so I'm going to subtract it from both sides, which gives me z times y squared minus 3. Last one is y squared over 3 plus x equals z over 1, or just equals z. I can cross multiply to linearize this, so I get y squared is z times the quantity 3 plus x. Now I have to divide both sides by z. There I am showing dividing both sides by z, which gives me y squared over z is 3 plus x. Now I have to undo the addition of 3 to x, so subtract 3 from both sides, and that gives me y squared over z minus 3 is equal to x. Okay, let's go to question 6. Now we're going to use guess method for all this stuff. So number 6 is a question that comes off the mechanics page of our reference table, page 6. We should have circled 4m over s, 12 kg m over s, and underline the word mass. So when I go to my reference table, I find that the lowercase v represents speed. So v is 4m over s. I look up, where is it? Momentum. They tell you the momentum is 12 kg m over s, so that's lowercase p. Little p is 12 kg m over s. And the unknown is mass. We know mass is little m. So we're going to use the equation P equals mv, but I have to solve it for m before I can proceed. So m is P divided by v. Now we're going to plug in the measurements and their units. Substitution step, 12 kg times m divided by s all over 4m divided by s. The m divided by s cancels, which means that I'm left with 3 kg because the 4 has 1 sig fig, so my answer needs 1 sig fig. Now we're going to do dimensional analysis on this. We don't do it for the given equation. We do it for the one we plugged into. So we're going to do the dimensional analysis on m equals p divided by v. This is our check step. So we're going to plug in. We got m in kg. We had p given to us in units of kg, m over s, and v was given to us in units of m over s. These m's over s's are going to cancel, leaving us with just kg on both sides. Number 7, we should have circled 8.5 m over s, 4s, and 6 m over s. Underline the word acceleration. This is also from the mechanics page, page 6 of your reference table. VI is the 6 meters per second. That is the speed that we started at. That's called our initial speed, 6 meters per second. 8.5 meters per second is the ending speed or final speed. We call that VF. Time period, T. Lowercase t is 4s. The unknown letter is A. Now, there's 2 equations you could have picked to do this. They are actually the same equation. One is expanded out. You could have used either this equation, A is change in V over T, or you could have used VF is VI plus AT. Either one, they will both turn out to equal VF minus VI over T for A, because a change is a final value minus an initial value. So that plugs in 8.5 m over s minus 6 m over s all over 4s. Now, order of operation says I have to do subtraction first. So the numerator gives me 2.5 m over s. The denominator is 4s. This has 1 sig fig, so I'm going to round the answer from the calculator to 1 significant figure, and that gives me an answer of 0.6 m over s, or m over s squared, either way. Now we do our check on the manipulated equation. Change in V over T is A. We just found A to be in units of m over s. Change in V, all velocities are m over s. T is an s, so both sides now check. Last problem comes from the electricity page of your reference table, page 4. You should have circled 0.5, capital A, 4.5 ohms, and underlined the word power. So based upon the variables on page 4, you should have identified capital I to be 0.5 capital A. Capital R is 4.5 ohms, and you were looking for capital P. The only equation on page 4 of your reference table which has those 3 variables is P is I squared R. So we're going to plug into that. That is 0.5 capital A. That quantity gets squared, and then we multiply it by 4.5 ohms. 0.5 has 1 sig fig. 4.5 has 2. So when we do the calculator work, you have to round to 1 significant figure, giving you 1. Units are capital A squared times ohms. Now we do our dimensional analysis on that equation, P is I squared R. We just came out with the units of A squared times ohms for P. I squared is in A squared. R is in ohms. Both sides now match. All right, last page with the graph. They ask you to graph the data, labeling each axis and titling your graph. Let's look at that first. And then in part B, we draw the line of best fit. I'll just show you that all at once. So the first thing we should have done is titled our graph. If you don't have a title, you would lose credit on tomorrow's test. But the title of this data that's being provided is velocity versus time, not time versus velocity. Now the y-axis should be in velocity in meters per second. The x-axis, time in seconds. Now scaling. Every line has to represent the same increment. I did every 5 lines on the horizontal had a value of 1 second. So I'm able to go from 0 to 5 seconds. On the vertical, I know I have to get to 110, at least. I think if you count it out, that means every line is like 5.5. That's a really awkward scale. So you would not use that. You go up from that. So like 10, that's what I did. Every line is 10. That's much easier to count by tens, isn't it? 10, 20, 30, 40, 50, and so on. That gets me all the way from 0 to 200. Now I plot my data points. I should see 1, 2, 3, 4, 5, 6 of them. Your data points could have been marked with little pluses, little X's, little dots, or little dots with little itty bitty circles around them. And then you have to draw your line of best fit. This should have been a line drawn with a ruler. It should not be connecting your first and your last point. That is not best fit. Just start and end, connecting them. Should go somewhere in the middle where you get some data points on the line. Like I got these two right on the line. And then I got a couple that are below and one above. Something like that. All right, let's go to letter A. What's the relationship? Tell me what that relationship is. Name it. Direct. Yeah. Now, if I asked you for the shape of this graph, what would you have said? Diagonal line. So the shape is a diagonal line, but that graph's relationship is direct. Letter B, now we're going to calculate the slope. You have to show me what 2 points you're using in your slope calculation that are on the line. Notice I chose this point here because I can read down easily and I can read over easily to get those values. This point I could not use. Why can't I use that data point right there? Anson? Right, it's not on the line, which means I can't use that data point and I can't use that data point. I also cannot use that data point. The question doesn't say find the slope of the data. It says find the slope of the line. The line. So you have to look at the line. Ignore the data points for all intents and purposes. That's why I'm using that one. And that's a great point because on my line, it comes down. I can read that value very easily because it's on a grid line. I know what the subdivisions are for each line. So that's an easy value to read. Same thing over. It's where two grid lines intersect. I'm going to use this one because my line did go right through that first point. So remember how we do this. We start by identifying our givens, which are the coordinates of the 2 points you circled and labeled. So my first point, your numbers are not going to be the same. Not unless you had a photocopy of my graph. So point 1 for me had a value of 0 seconds and 10 meters per second. My second point on the line was 2.8 seconds and 70 meters per second. So I want to find the slope. That's letter M, or you write out the word slope. The equation for slope is slope equals y2 minus y1 over x2 minus x1. You do have to tell me what y2 minus y1 over x2 minus x1 equals. So if you leave off that, what I just covered up, and that's all you wrote on your test, you do not get points for the equation step. That isn't an equation. That's an expression. The difference between an equation and an expression is that an equation equals something. You have to tell me what it equals, okay? That's particular from New York State. So now we're going to go ahead and plug in. There are my points with the units being attached to them, 70 m over s minus 10 m over s, all over 2.8 s minus 0 s. Now I do order of operations, which means I'm going to subtract first, giving me positive 60 m over s all over 2.8 s. Now my numerator has only one sig fig and my denominator has 2, which means when I work this out, I want only one significant figure on my answer, but I need a sign on it to tell me which way this is sloped, up or down, and units. With one sig fig, I get positive 20 m over s over s. Now, part C wants the equation for the line for this graph. We start with y is mx plus b. We're going to change the letter y to velocity. We're going to change the letter m to positive 20 m over s, or whatever you got right here. I expect to see that plugged in directly with units and a sign. X is the variable time, and then we go to our graph. We read the y-intercept. I'll be reading yours when you're asked to do this. And I got 10 meters per second for my y-intercept. Okay, that was the review. What do you want to go over on the review? Yep, Jan.
Go over questions 6, 7, 8.
Yep.
Just that type of question.
Do you want me to do a different one?
Yes, please.
Okay, so these are okay, though. You were able to follow what I did.
Yeah.
Okay, let's try another one. I'll make up one. Grab some paper. Got your reference table? How about this problem? You can write this in your notes, or is the back page of the Unit 1 packet blank? No, it's not. So in your notebook is where you would do this. So an object experiences a 4.2 N net force and accelerates at 2.1 m over s squared. What is this object's mass? So this could very well be a question on tomorrow's test. The difference on tomorrow's test is there would be directions at the end of this as a constructed response problem. And let me go over what those directions would say. The directions would say, show, and it would be in brackets or parentheses, show all work, including the givens, unknown, equation, algebraic manipulation, and substitution with units. And then it would also say, express your final answer with appropriate units and significant digits. Very, very specific directions. I think you can agree that's extremely specific. Anything that is mentioned in here is being graded, and you're being given a point for each of those things. Okay, when we finish going over this, I will show you how many points this question is worth on a constructed response out of 100. And I'll tell you right now, your test tomorrow has 2 parts. Every unit exam I give has 2 parts. The first half is multiple choice. There will be 10 multiple choice, half of the test. So that's 50 points out of 100 comes from multiple choice. That's either right or wrong. You either can pick the right answer or you can't. The constructed response is where you can get partial credit for showing all of these things. Okay. But if you miss a step and don't show me something I asked for, you're losing points. Because I'm telling you, this is what I'm grading right here on your answer paper. Okay. So let's go over, first of all, as a guess method type of question, which that's what this is, we would have this value given to us, this value given to us, and we're looking for that. So let's start with our givens. That way I can kind of check off as I go. Let's look at our reference table. Which page of the reference table do you think this question would be coming from? Which section? Is that electricity, waves, modern, geometry and trigonometry, or mechanics? Hanson? Yeah, it's mechanics. That's the only page that talks about accelerations, masses, and net forces. All right, so let's start with this value of 4.2n. Bless you. What are we going to identify that as? Use page 6 of your reference table. What variable is 4.2 capital N? It says in this question that 4.2 capital N is a net force. So what's the symbol for that? F net, F subscript net. That's what you write. Okay, the next given measurement is 2.1 m over s squared. What does the question tell you that is? That's an acceleration. What letter does your reference table say you use for acceleration? Lowercase a. Okay, so now I've got my givens. Check. All right, now I need my unknown, which is the word mass. According to page 6 of your reference table. What letter is that? Little m. Check. All right, now we need the equation, which has the F net, the A, and the M. Look down the equation side of the page. What's the equation that has all of that? If you're not practicing doing it now, probably you won't be able to do it tomorrow. Lucci?
A equals F net over M.
That's it. This equation, by the way, is known as Newton's second law of motion. We'll be talking a lot more about this equation. We spent about 4 days, maybe 5 days, almost a week, just on this one equation and concept. So let's go ahead and check that off. We did our equation. Now, notice I said algebraic manipulation. The reason I said that is because it is not solved for the unknown. So you got to move it around to solve it for m. First step is multiply both sides by it. And then you divide by the A. So you should have given me m is F net over A. Okay, check on the algebraic manipulation. Now I need to do my substitution with units. So m is the value of F net, which is 4.2 capital N. A is a value of 2.1 m over s squared. Okay, check on substitution with the units. Now, final answer with units and sig figs, which means you're going to go to your calculator. Divide that out. What do you get? I'm good at arithmetic. I already know what the answer is. That's why I picked these numbers. 4.2 divided by 2.1, calculator says is what? Hello, I can't hear you. 2. Okay, does that have the right number of significant figures? No. How many do I need? So what are we going to write? 2.0. Now, what units are you going to put on that? Capital N over m over s squared. That's it. Because that expresses the final answer with units and significant digits. That would be a question like that. Let me go over how many points this is worth. You ready? You're going to be like, oh my God, that's that many points. 1 point for that correct given. 1 point for that given being correct. 1 point for the unknown being correct. 1 point for picking the right equation off the reference table. 1 point for correctly doing the algebraic manipulation to get you to m is F net over A. 1 point for doing the substitution. 1 point for the answer from the calculator. 1 point for having the correct sig figs on the answer. And then you're going to get 1 point for having units on all numbers everywhere. Which means if I had left off that n right there, this point is gone. It's either all right or it's not. Even one mistake with a unit costs you that unit point. So how many points is this question? 1, 2, 3, 4, 5, 6, 7, 8, 9. That is a 9-point question out of 100 points. Now, did I do any dimensional analysis with this? The dimensional analysis would be a follow-up question. And the dimensional analysis would say, using dimensional analysis, show that M has the same units as F net divided by A. And this would be, I don't know, let's work it out. How would we do this? We would start with M equals F net divided by A. Then we would change, I said A and I wrote M, F net over A. I would then change everything to their units. M I got in N over M over S squared. F net I would change to capital N because that's what it was given in. And then I would change A to M over S squared. And that works. So let me tell you how many points this is worth. 1, 2, 3, 4. It's worth 4 points. This is a 4-point question. 1 point for setting up the equality. 1 point for showing me the correct unit for M. 1 point for correctly showing me the unit for F net. And 1 point for the correct unit for A, getting that all to match up. That's 4 points. So together, if I asked you both of those back to back, it's 13 points out of 100. So if you don't know how to do either one of these, the highest grade you could possibly earn on this test is an 87, and that's not likely. Because if you don't know how to do this, you probably don't know how to do a lot of other stuff that you're being asked to do on this test tomorrow. Brayden, you have another question? Does this make sense, what you have to do? Okay. And now you've seen the wording of how these problems are set up. Anything else you want to ask? Anything at all? Yes, is that good?
For 5C, do you have to write the multiplication?
No, you don't.
And for 5D, do you have to like y2 minus 3z all over z?
What did you just say? Y squared.
Y squared minus 3z all over z.
So that's the same as y squared over z minus 3. Yeah, that's the same thing. Yep. Either way. Anything else? Okay. Then we're going to go back to Unit 2. So could you please pull out your notes from yesterday from Unit 2? Let me just put some stuff away here so I don't lose what I'm doing. This is where my notes were from yesterday. All right. And just to, let's see, notebook, reference table. We're going to need our Unit 2 packet now. Calculator, pencil. You will not need a ruler today. On Thursday's class, you will need a ruler and a protractor. Okay, so for Thursday, make sure you bring a ruler and a protractor to class. We'll be making a lot of drawings starting on Thursday that are to scale. All right, when the bell rang yesterday, we had gotten through the concept of a position. We defined what a position was. And we got to the point where we were starting to talk about how we can identify the directions on vector quantities. And one of the ways we said we can do that is with words. Words like right, left, up, down, in, out, forward, backward, north, south, east, or west. The second way that we can specify the direction on a measurement is with a sign. And when I say a sign, I mean either positive or negative. Now, the thing is, positive and negative is not very specific. It's not very precise. So what we will often do, well, let me explain to you what that means. Positive is usually code for either something going right or up. It's either one. How do I know something went right versus going up if I put a positive on it? I don't. Okay, and that's why it's not very specific. But sometimes it works out very well for us when we're doing some mathematics with it to put the plus or minus. Minus would therefore translate to either left or down. Okay. And then the third way we can specify direction is with an angle measurement. Angles are the most precise way, and this would be in degrees. Now let's talk about how we measure angles. Our convention is that we start at the positive x-axis. You're going to go counterclockwise around the origin. That is the rule for measuring angles. Okay. Let's do some review, therefore, on this XY axis that we have drawn here. Zoom out just a little bit. Okay, can we all see this here? All right, so let's start at our positive X. Positive X sometimes can stand for east. Positive Y could stand for north if we're doing a compass rose. Negative X would mean west. Negative Y would mean south. That is if we're drawing something. I can't tell you how many times a question has said a student walks 3 meters east. And then when you're asked to draw it out on the paper, I don't see an arrow pointing right. I see an arrow pointing left for east. That's not correct. East is to the right on your paper, okay? Please make sure you understand those compass directions. Let's talk about angles. Since we're going to start at the positive x-axis, the positive x is our 0 degree angle reference. We go counterclockwise, which this is our counterclockwise direction, until we get to north, which means positive y is equal to 90 degrees because there is a right angle between those axes. If I continue going counterclockwise around, I end up at the negative x-axis, which has a value of 180 degrees. I keep going around counterclockwise till I get to the negative y-axis, whose value would be 270 degrees. And I can keep going till I land back at the positive x. And if I've done that, I've rotated through a full 360 degrees, making a circle. Now, very often when we talk about angles, we'll be asking you what quadrant is this in? Oh, do you remember your quadrants from math? You've done this before, right? This is not new. It should not be new. This is quadrant 1. This is quadrant 2. This is the third quadrant. And this is the fourth quadrant, okay? Now, the reason I'm bringing this all up is because we're going to be using this to help us do some displacement calculations in a minute once we define what that is. Let's take our break, and when we come back, we'll continue with this discussion.
I redid my lab.
Great. I will take that and regrade it. Thank you.
Okay, no, we said tomorrow, period 7. So Friday, would you mind doing that to Friday? I'll send you.
All right, ladies and gentlemen, let's get back to this. So this is all being used to help us understand vector measurements where we need direction, in addition to how far or how big something is. So let's now talk about another vector measurement, which is called displacement. The term displacement refers to the change in an object's position. The change in an object's position. Since position is a vector measurement, it means that displacement is also a vector measurement. It is also a vector measurement, meaning it will have not only a magnitude, a size, but it also has a direction. It has both a magnitude and a direction. Now, the symbol that we're going to use to represent displacement is a lowercase d. I think you can understand why we're using d, right? Displacement d. But to indicate it is a vector, we put an arrow over the top. We use this little arrow notation to tell us that it has to have a direction. Got to point in some way. The units that we measure displacements in the metric system are meters, which we abbreviate with a lowercase m. Now let's do a couple of examples, okay? Let's start with an example where I have an object on the x-axis. And let's say that is the origin right there. Let's say that the object starts here. And let's say that is the 1 meter position. I'm going to call that the initial position. And they walk this way until they get to the 5 meter position. This is their final position. I'm going to mark that with an F, F for final. So I means initial or starting point. F stands for final or ending point. This arrow that I just drew represents the displacement, how far the object's position changed. Now, the way I would find this displacement is by taking the final position on the x-axis. Remember, position on the x-axis is x. It's like I'm looking at the x-coordinate, the final x-coordinate, and I'll subtract the initial x-coordinate from it, which means that I would take positive 5 meters because we end up 5 meters to the right of the origin. And then I would subtract positive 1 meter. Why is it positive? Because we started off a meter to the right of the origin. Now, when you subtract that, what do you get? Positive 4 meters, which really stands for 4 meters to the right. This object was displaced 4 meters to the right. 4 meters to the right is a better answer than positive 4 meters. Just because I don't know what the positive really stands for, right or up or out or forwards or east or north. It's too vague. But it is helpful to write these positions when I do it as positive, so that way it's easy to plug into the calculator. It would not have been wrong to write 5 meters right minus 1 meter right. But how do you type in right on your calculator? It's just easier to do it with the signs to determine it mathematically. Are you with me on that? Okay, this is example number 1. Let's look at a second example, which is much more complicated. Here's the origin. Let's say I start off with an object here. And these are going to be in meters, okay? This is the initial position. Right there. That is the initial position I. 1, 1. 1 meter, 1 meter. Positive 1 meter, positive 1 meter. The object ends up here. That is 5, and that coordinate is 4. And these are also in meters. That is the final position. Now, what I'm going to do is figure out how far the object was displaced in both the x and the y directions. So I know my initial x position was positive 1 meter. My final x position was positive 5 meters, that means my displacement in the x direction, which I'm going to now say is d with the arrow, subscript x to mean along the x-axis, that would be positive 5 meters minus positive 1 meter. So that gives me the positive 4 meters, or the 4 meters to the right. Isn't that the exact same thing I just did in the previous example? What's different is that they're not in line. One is above the other on the y-axis. So we're going to do the same thing in the y direction. The y positions are written as yi and yf. These are the y coordinates. My initial y coordinate is positive 1 meter because I'm above the horizontal axis by a meter. My final y position is positive 4 meters. So I can find out how far I was displaced in the y direction by doing positive 4 meters minus positive 1 meter. What's that going to give me? How much? Careful. What does it need? Besides the 3 meters, it needs something else. The positive 3 meters, or you could say 3 meters, comma, up. That's right, because this is in the y direction. Notice there's 2 parts to it. That's actually not the final answer. These are parts of a final answer. Let me show you what we do with it. Come back up to this picture. This is the displacement in the x direction. We just found that to be 4 meters to the right. But then we just said we went up 3 meters. So that is the displacement in the y direction, 3 meters. The actual displacement is this arrow from the starting point to the end point. That is the vector I need. Okay, look at what I just ended up drawing. What is that I just drew? A right triangle. How do you find that side of a right triangle? By the way, what is that side of the right triangle called? The hypotenuse. Do you remember how you get the hypotenuse of a right triangle? That is correct. So what I'm going to do to find the magnitude of the displacement is I'm going to use a squared plus b squared equals c squared. Using the variables on the triangle, that would be d in the x direction squared plus the displacement in the y direction squared, giving me the displacement that I'm looking for squared. Now, I picked these numbers on purpose. So this is 4 meters squared plus 3 meters squared is the displacement squared. I think many of you know what that displacement is right away. It's probably the most famous Pythagorean triple that exists. You have a 3, 4, what right triangle? 5. So the displacement's magnitude is 5 meters. That's just its magnitude. Now, is displacement just a magnitude? Does it just have a magnitude? No. What else does it have to have? Okay, right? So now we got to figure out in what direction is that arrow pointing. We can't use a word for that because it's not up. It's not right. It's not positive. It's not negative, so I can't use a sign. My only other option is to use the angle. And do you notice that that arrow is pointing in quadrant 1? It's pointing up and right. That's a quadrant 1 angle. The direction you're going to give me is that counterclockwise angle right there. We have to calculate it. Okay, let's review how we find angles like this. This goes back to right triangle trigonometry. If I were to label the sides of the triangle the way I learned it back in the 1980s, I would call this side of that right triangle the adjacent side, ADJ. This side opposite the angle, the one that's created by the opening, is called the opposite side. And you already told me that that side is called the hypotenuse, HYP. So A, O, and H. You learned a phrase when you learned right triangle trig with these trig functions. Do you remember what that phrase is? SOHCAHTOA. Let's write that down. SOHCAHTOA. Now, when I went to school, we were not PC about this. And my math teacher said it was an Indian chief, native, indigenous Chief SOHCAHTOA, was it? Anyway, that was not PC back. We didn't care about anything PC back in the 80s. It was just everything was irreverent. Now, cannot say that. We just have SOHCAHTOA. And somebody once said to me that was not appropriate either. I had a student teacher many years ago. He goes, that's not what we. I'm like, well, what do you say? I don't know. Have you learned it any other way than SOHCAHTOA? No other mnemonic for it, right? That's why I'm like, I don't know where this guy came from, where he said that's not, if this was offensive to somebody saying SOHCAHTOA. I'm like, what? Like, who's offended by SOHCAHTOA? I know people don't like to use it, but what else do you call it? Okay, so anyway, look at the triangle for a minute. I guess I'm just old. Look at the triangle. What sides do we know? Now we do, but let's pretend we don't know the hypotenuse. We know the opposite and the adjacent, the O and the A. Look at the trig functions. Which one has the O and the A? This one here, the TOA piece, which means the equation we use is that the tangent of the angle we're looking for is the opposite side length over the adjacent side length. Now we're going to have to solve that for the angle. How do you get rid of a tangent function from one side of the equation? Anybody know what you do to get it from one side to the other so it's not with the angle anymore? It's actually a fairly obvious answer. You can't divide it because these are not multiplied. This is inside of it. So the opposite of tangent is inverse tangent, which is on your calculator. Tan to the -1 power. So here's what we do. We end up getting the equation for the angle that is the inverse tan of the opposite side over the adjacent side. Okay, that's what we end up doing. Does that ring any bells? You've seen inverse tangent before? Okay, so in this example, to get the angle we want, we're going to do the inverse tan of the opposite side, which is dy, over the adjacent side, which is dx. Which means we're going to do the inverse tan of 3 meters over 4 meters. Okay, now do you know how to type that into your calculator? The first thing I need you all to do is check your mode. Check your mode. You need to be in the degree mode. If you have a scientific calculator, it's on your display, and you can change it by hitting the DRG key and go between degrees, radians, and gradient measure. We want degrees. If you're on the graphing calculator, hit the mode. It should say degrees, not radians. If it says radians, arrow it over to select degrees, okay? So now how do we type this in? We get this tan to the -1 power by hitting the second key first and then tan. So second tan gives us the inverse tangent. And inside the parentheses, these meters are going to cancel. So we just do 3 divided by 4. And there's my answer. Now, do I want all those digits? No way. You know that. You know better by now. I do not want all those digits. We always round to the nearest degree. So if I round that to the nearest degree, how many degrees is it? That says 36.8698965. So how many degrees is that? 37 degrees. That's what you're going to give me for the answer. So this direction is 37 degrees. So my final answer for the displacement in this question is 5 meters, comma 37 degrees. That's about as precise as we can get. That is a very exact change in position. I know exactly how far up from the horizontal axis I moved and by how much. Okay? That's displacement. The last term we have to talk about is the term distance, which is super easy. Distance just refers to how far an object traveled. Total. How far did you move? Now, distance is what we call a scalar quantity. It's a scalar measurement, which means it has only a magnitude. There is no direction associated with it. It's just an amount. The symbol we use for distance is just lowercase d, but no arrow on it because it is not a vector. A vector would have the arrow over the top. And with the arrow over the top, it's not distance, it is displacement. That's right. And the units that we're going to measure this in the metric system are also meters, which we abbreviate with a lowercase m. So let's try an example, okay? Positive x-axis. Object starts here, goes this way, and then reverses and ends there. Here is the initial position. That is the final position. My question is, what is the distance this object traveled? In other words, I have to add up the lengths of those arrows. Add up the lengths of those arrows. So the arrow that points to the right is how long? From 0 to 5 meters is how much? 5 meters. From 5 meters to 3 meters is how long? 2 meters. So how much distance did this person cover? 7 meters. Now, if I wanted the displacement, we would do something different. We take the final position, which is positive 3 meters, and we would subtract the initial position, which was 0 meters. So the displacement would be positive 3 meters or 3 meters to the right. I'm doing this as an example so you can see that the magnitude of my displacement doesn't necessarily equal my distance, especially when you change directions. Okay. Go back to example 2 on the previous part, this right here. If I had a person walk from here to here and then here to here, how much distance would they have covered? From here to here to here, how much distance did they travel? 7 meters, 4 meters plus 3 meters. That's it. It's nice. No trigonometry involved because you're just adding sides. Okay? All right, one more last thing before we try some practice in your packet. I want to quiz you. Tell me if these are distances or displacements. I'm going to give you just measurements. Throw them at you. What is that? 2 meters. That is a distance, D. How about positive 2 meters? That's a displacement. How about 4 meters north? Displacement. How about 5 meters at 125 degrees? That's a displacement. All three of those have a direction. That one does not. Okay. Good? Okay, let's go to your packet. And in the Unit 2 packet, I want you to turn to page 3. Got a bunch of examples here that we're going to work through. And I want you to turn to page 6 of your reference table for a quick minute. We're going to check off things as we learn them on the mechanics page. This is where we start the course. It's going to get us to like end of January. The letter we learned today was the letter D. Let's check that off. Notice the reference table tells us that lowercase d can represent displacement or distance. We should know they are both measured in meters. But displacement is the vector. So I'm going to put an arrow over that word to remind me that that's the one that has to have the direction when I use it. The reference table doesn't put D with the arrow is displacement. They just say it's, you can use it either way, but you have to know which is which. Which one is the vector, which is the scalar. Okay, so you're going to see we're going to add some codes to this to help us as we learn things. A lot of these practice questions, we draw sketches for things. They're pretty easy to do. Let's start with question 1. We have a cart that goes 2 meters to the right, and then it goes back 1 meter to the left. Can you sketch that? Go 2 meters to the right, and then it comes back 1 meter to the left. That would be my sketch. First thing I want to know is the total distance. Distance is lowercase d. How would I get that? I would add those values. 2 meters added to 1 meter. How much distance did this cart roll through? 2 meters plus 1 meter is 3 meters. Now I want to know the displacement from the initial to the final position. Here is the initial position. That is the final position. Here's how we can figure it out. We can take that we moved 2 meters to the right, or positive 2 meters, and we can add that to 1 meter going left, which is negative 1 meter. So you see, I did very much like what I do for the distance calculation, but I include the directions as signs. And then I just do the math. What is that going to give me? I know the number is 1 meter, but what has to go out front? A plus or 1 meter to the right. The positive sign here means to the right. Let me know if I've lost you. Number 2, we have a child observing a caterpillar walking on a windowsill. And the caterpillar walks 18 centimeters to the left, and then it goes 6 centimeters to the right, and then it goes 10 centimeters to the left. I want us to make one change to the numbers. Please put a decimal point after the 0 and 10. So that way all the values are significant to the ones place. Can we sketch that? Let's do that right here. 18 centimeters left, then 6 centimeters to the right, and then we're going to go 10 more centimeters to the left. So the first question wants to know the total distance. That's D. Anybody tell me how you're going to get the answer? I don't want to know what the answer is. How do you get it, Braden? So 18 cm plus 6 cm plus 10 cm. All right, go ahead and add them up. Anybody? What is it? That's right. 34 centimeters is correct. You can use your calculators. You have them. Use them if you want to. Next, I want to know the displacement. So we're going to tackle this like we did the last question, but we're going to add signs to things. So this 18 centimeters is going left. What sign is left? Negative. That's right. Negative 18 cm. The 6 centimeters points to the right. What sign is that? Positive. How about the 10 centimeters going left? Negative. So negative 10 cm. What's that going to give us? You got it again, Liam?
Negative 22 cents.
What does that negative mean? Yep. Very good. These are the easy ones, okay? Because they're all in one line. So they're easy. We can just handle it with straight addition with signs. Number 3, this one's a little different because we're going to throw something up in the air. It says we're going to throw a ball upward from an initial height of 1.5 meters. The ball reaches a height of 5 meters and then it falls to the ground. I want to know what's the total distance traveled by the ball. Let's sketch it. I'm going to do my sketch over here. This is the symbol for the ground. Horizontal line with these hash marks. This represents the ground. Where does the ball start? It starts above the ground by 1.5 meters. So this is my initial position, and I know that distance right there is 1.5 meters. I'm going to throw it up into the air until it gets here. But then the ball is going to come down and land on the ground. From here to the ground, we know is 5 meters. Can we make that 5.0 meters, please? 5.0 meters. Okay, so there are really 2 arrows in this question. One going up and one coming down. How big is the arrow going up? Yeah.
3.5 meters.
Yeah. 1.5 plus the 3.5 would give us the 5. That's right. So to come up with the distance, the ball is going to travel 3.5 meters, and then it's going to do another 5.0 meters. So Aiden, can you tell me how much distance the ball travels? Very good. Now, how do I do the displacement? We have to add signs to those numbers. Angela, can you tell me what sign I'm going to put on that 3.5 meters? Yep, up is positive. Very good. Alucci, can you tell me what sign I'm going to put on the 5.0 meters? Yep, because that's in the downward direction. Eileen, can you tell me what that means the displacement is? I'm sorry? Yeah, 1.5 meters down or negative 1.5 meters. Very good. All right, number 4 is a little trickier. They're giving us like a miniature graph grid to draw this out. The path from the subway station to the art museum goes 3 blocks north and then 4 blocks west. So let's sketch that out. Let's say that this box here is, that dot is the subway station. We have to go 3 blocks north. North would be up on the page. So each block is 1 box, 1, 2, 3. That arrow represents 3 blocks. And then we have to go 4 blocks west. West is left. 1, 2, 3, 4 to here. So this dot is our final destination, which is the art museum. And that was 4 blocks. I want to know what's the straight line distance going from the subway station to the art museum. That means I want to know that distance right there from here to here. We would call that the magnitude of the displacement. What figure did we just end up drawing? How do you come up with that side? So 3 blocks squared plus 4 blocks squared gives us the displacement's magnitude squared. That is the straight line distance. So what's the displacement gonna be? It's a 3, 4, 5. Again, 5 blocks, just like the example we did a little while ago. So far, so good? Yes? Okay. Can we turn the page? When we look at a map, a student realizes that Birmingham, that's Birmingham, Alabama, is nearly due west of Atlanta, that's Atlanta, Georgia, and Nashville, as in Nashville, Tennessee, is nearly due north of Birmingham. If the distance from Atlanta to Birmingham is roughly 150 miles, and the distance from Birmingham to Nashville is roughly 200 miles, what's the estimated distance from Atlanta to Nashville? So we got to sketch this out. I don't know how you would do this otherwise. I picture a map. Where are these points? Where are these cities? I'm putting like pins in them. So let's do that. Birmingham is nearly due west of Atlanta. Nashville's north of Birmingham. All right, so let's say this is Atlanta. Birmingham is due west of that. That means it's to the left on our page. This would be Birmingham. How about I just put a B? I'm not going to use words. A for Atlanta, B for Birmingham, and guess what I'm going to use for Nashville? N. Yeah, Nashville is north of Birmingham, due north, so straight up. Now let's label the distances. It tells us that from Atlanta to Birmingham is 150 miles. So that is 150 miles. And Birmingham to Nashville is 200 miles. Obviously, I did not do this to scale. What is the distance from Atlanta to Nashville? That would be a displacement, but I just want to know how big it is. Any ideas? What am I going to do to get it? Yeah, another Pythagorean theorem problem. So here I'm going to take 150 miles, square it, add it to 200 miles, square it, to give us this displacement value squared. Without the square. Let's go to the nearest mile, okay? Go ahead and work that out, please. Who has it? What is that distance? Hanson? I agree. How many of you got that when you did the math? Very good. 250 miles. Let's just, I think we're going to stop. I'm tired. I've been talking a lot today with all that review. So we'll stop there. We'll pick up with more of this on Thursday. Remember, on Thursday, you got to have your ruler and protractor here. Because instead of using Pythagorean theorem, we're going to learn how to draw it out to scale. Which without our, and then you don't need inverse tangent formulas. You don't need any equations. You're just measuring. But if you don't do it to scale, it doesn't work out. You got to learn how to make those pictures to scale. So make sure you have your ruler protractor here.